Good morning, ladies and gentlemen. Thank you, Stefan. We are two presenters, actually.
There's only one on my
Don't worry, it's all right. My name is Isabel González, anyway. And I come from Spain, too. I'm an industrial engineer. And I work as a project manager, and I'm coordinator of IP within our company. We are here to present the work of our team about the application of linear motor technology for variable speed transportation systems. First of all, we are going to give a brief introduction about the urban transportation challenges and trends today, to start talking about accelerated moving walks, what they are and what are their main applications, then to give a brief explanation about linear motor technology and how can we apply this technology to our systems. 20th century has been characterized for many changes. Urban population has increased from 10% to almost 50% in this century. And this trend is still ongoing today. In 2012, 3,700 million people live in cities, and 2050 reports estimate that this quantity will increase up to 6,000 million people. This means that 70% of the total world population will live in cities. Of course, this means that there will have to be a change. Cities will have to be planned in a different way. They will have to be accessible and interesting for both, for people that are visiting and for inhabitants. So these cities will have to be planned for people, for business, for security, and for high environmental standards. Cities, as we know today, are mainly based on cars. We cannot understand to live without a car. But car is not a universal means of transport, and we all know there's congestions and to be in a queue for a long time. And cities will have to increase the size and will have to move vertically. The ultimate goal is to make use of the urban transport. And for urban transport, we know many ways of them, but they will change too. So the airplanes will be used for long distances, for intercontinental distances. Fast speed trains will be used for long distances by land. And to link cities with the others, we'll be using high speed trains again and metros. The individual transportation will not be known as today. So they will be only to cover the last few miles and always in a shared basis. We all know these sort of cities. Now there are only a few of them, but there will be more in the future. And they will have different layers for transport. One at the street level as of today, and underground as many of the cities today, but there will be a third level above street level. And this will be mainly for pedestrians. All those levels will be connected and mobility will become 3D. Talking about public transport, we all know all of this difference. They have some advantages from the ecological point of view, from the economical point of view, and most of them can be applicable, of course, in all ranges, but are more adequate for some ranges. For example, we have identified that for short distances, the most effective way of moving high amount of people are the moving walks. Why short distances? Okay, they have a limitation, that is the speed, and it's due to safety reasons. But they have some advantages. There's no waiting time, continuous systems. We talked yesterday plenty about the waiting time. And the other advantage that they have is in the case of a breakdown, everybody is able to walk. We don't like to do it, but we can do it. Okay? Talking about longer distances, like for example 2 kilometers, in the range of between 1 kilometer, 2 kilometers, we will go to automatic people movers. They have the big advantage of the speed. You are in an enclosed environment, so there's no danger. We don't have to change from one standing place to a moving one. But the limitations are the capacity. We can increase the capacity, of course, as much as we want, but then the infrastructure required will be much higher. And the other one is in case of a breakdown, we need to walk. And we need stations. They are not continuous systems. So there is a gap here. We have a gap between 200 meters and 500 meters that, as of today, is not covered. And if we want to increase the capacity, the gap could be extended even over. So we were thinking, how can we fill this gap? And we found that one answer could be an accelerating system, accelerating moving walk. What is it? It's a moving walk with the same capacity as a moving walk, but that can reach higher speed, 3 to 4 times the speed of a standard moving walk. We are not the only ones that think that this is the target for tomorrow's transport. Many other manufacturers have some attempts in the past to cover this gap. For example, in the 19th century, there was some attempt already, and this was the first known attempt of achieving a variable speed system, and it was a real unit installed in Paris exhibition in 1900. The working principle were different platforms that were moving at a different speed. There were belts, conveyors moving at a different speed, and the way to accelerate was to change from one to another laterally. It was working for quite some time, but it was finally closed, and there was not an attempt to improve the system. Later on, in the 1960s, there is a patent by Bulaton and Suppinger that was based in some platforms that had a rhomboidal shape and they're moving laterally to achieve acceleration. This gave an S shape that carried to a high-speed one. Some manufacturers later on realized this concept into real prototypes, but as far as we know, they were not open to public, so they were prototypes. The main issue with this seemed to be the S shape. So to achieve a place where to install this unit could be a little bit difficult. And there is not evidence that they could solve the problem of a handrail moving at the same speed as the platforms. In the 1990s, there were units installed at Brisbane Airport that had accelerating systems, and the working principle were different belts running at a different speed. So the way to achieve acceleration was to change from one belt to the next one. The handrail had exactly the same principle with different handrails running at a different speed. This was a success. It was running at Brisbane Airport and was servicing in a public environment. And this was probably the first test that showed that really this could be applicable in a public environment safely. Unfortunately, the unit was finally closed, and today they are not working. The most ambitious product that was in a commercial environment was this one in Montparnasse station in Paris. It was based again in continuous belts, threaded belts, running at different speed, and the transition from one to the next one was made by rollers running at different speed, every time faster. So you could make the transition in a gradual way from one speed to the next one. And this was the first variable speed handrail that was installed in a public environment. It was based on some rigid, fixed distance, fixed length handrails, and then some part of the handrails that were flexible. They were adapting the length depending on the kinematics of the system. Of course, there are many more of them. There are many patents regarding these accelerating systems. So it seems that it's a trend. And to find a real product that could be working and safely in a public environment would mean that we could somehow cover some of the challenges of the futures of the cities of the future. And now Albert is going to talk a little bit more about that.
Thank you very much, Isabel. So, up till now we have identified that there is a gap in public transportation system that can be covered by acceleration moving walks, and we have seen several examples of companies trying to reach this gap with different concepts. Some were more successful than others. But if we have to think about how to design an acceleration moving walk, the first thing we have to talk about is safety. And why can an accelerating moving walk be less safer than a conventional moving walk? And the main reason is speed, of course. So for conventional moving walks, speed is limited because there is a relative movement between the fixed part when you enter and exit the moving walk and the speed that is already moving, the area which is already moving. And the limitation in speed depends a little bit on the codes, but normally it's 0.75 mainly. Some people don't like moving walks to be so fast because they want them to be used by childs, elderly people without having incidents. So what if we can do an accelerating moving walk that only has relative movement between the fixed part and the moving part in the entry area, and then we accelerate continuously so there is no other relative movement between moving parts. To do so, the first thing we have to do is to take into account that the acceleration and jerk values have to be controlled. There are many studies about which should be these values. For example, a person can keep the equilibrium and the balance for accelerations lower than 0.5 meters per second. Also, jerk has to be taken into account for comfort. And because to achieve this variable speed, so because normally the systems, the concepts to achieve this variable speed involve that exposed area for the passengers is changing. So there is relative movement. We should use slotted surface, combs, and teeth to avoid any risk of entrapment. So the only design currently that has these features and is open to public is the TurboTrack moving walk made by Thyssen and installed in Pearson Airport in Toronto. The working principle is not very complicated. The pallet is comprised of two bodies instead of only one. There is a short body and a long body. When you enter the moving walk, you only see the short bodies all around. When the speed starts to increase, short body in the front starts to go faster, so there is a gap in between, and the long body starts to appear. Of course, there is a comp system to avoid any entrapment between those two parts, because when you go into the exit area, the long body starts to disappear, and you have to go back to the short body. The relationship between the speed in the entry area and the speed in the high speed area is the relationship between the distance of both bodies. And the handrail system is quite the same. When you enter the moving wall, there are only grasps. There are small parts you can handle too. And then when they start to separate to each other because the speed is increasing, there is another part underneath. It's called a cover, and they are meshed and slotted together. Of course, when you approach the exit area, the cover disappears, and you only have grasps again to hold your hand. Grasps and short pallets are synchronized together. And how is that achieved? All the system, all the power transmission, all the movement relationship, they are all made mechanically, pure mechanical. So there are big motors there. There are a lot of chains, shafts, gears, sprockets, and so on, giving movement to all the necessary components. In the high-speed area, the pallets are linked to a high-speed chain that is moved on the turnaround stations, and when the pallets reach the exit, the deceleration and acceleration area, they disengage from the high-speed chain, and they engage in a variable speed, in a variable pitch endless screw. This variable pitch means that every turn of the screw means a different distance the pallet is moving. So controlling this variable pitch, you can control the acceleration. The handrail principle is also quite the same. Covers the parts that appears during high acceleration parts and during high speed parts. They are linked to a chain, and they are running all the time at high speed. Grasps are driven by them. They are connected in the high speed areas, but then when you go to the deceleration areas or acceleration areas, they are disengaged from there, and they engage to a variable pitch screw. Of course, variable pitch of the pallets and of the handrail, they have the same pitch at every time, so they are synchronized. But at the end of the day, all the power, all the transmission of movement is made from a main drive shaft and using gears, sprockets, and so on. So the question is, this is the system that exists at this moment, but is there any technology that can enable us to think different, to move all the components in a different way, maybe simplifying the system, maybe moving linearly the pallets straight ahead and controlling its speed without the need of so many components? And our research has shown that there is a technology that can enable this. And this technology is a linear motor technology, or to be more precise, linear synchronous motor technology. You may be aware of this technology. It has been used for several years in several businesses, for example, high-speed trains, also milling machines. But also there are another applications you may be not so aware of, like for example, roller coasters or aircraft launch systems in aircraft carriers. Why is this technology used in these businesses? Because it has some advantages, like high acceleration rates, and also it allows a very accurate control and positioning of the things you are moving. The technology behind it is quite simple. A linear motor is a rotational motor that you cut and lay flat. So that instead of having a rotor, you have a track of magnets. You use permanent magnet materials with alternating poles. And instead of getting a torque, you get a linear movement, allowing you to get a direct, you get a linear force, allowing you to get a direct linear movement. And the advantages of having such system is that you can have a very accurate positioning and response of the system, smooth and controlled motion without velocity ripples, and also high peak force to inertia ratios. And because there can be no contacting surfaces, you have no friction force and no wear of the components. This sounds very good, but there are challenges to be solved to apply this technology on variable speed drives and acceleration moving walls. The first one is how to wire the parts, how to provide current to the motors, and also how to manage the air gap, because air gap is the distance between the coils and the magnets that's affecting the force you get and also the efficiency you get. So in this kind of system you have a lot of mechanical components, guides that need adjustment, and also you have a lot of tolerance that play a big role. Okay, so we made a research, we saw this technology may be feasible, but first you have to select which of the different motor construction types is better for this kind of application. And there are two main ones. One is the iron core motors and the other is the ironless motors. In iron core, there is an iron, a magnetic material inside the coils. That means the magnetic field is higher. But as a result, there is also an unbalanced force, non-compensated force, that allows, forces you to have a robust guiding system and also add this friction. On the other side, this strong magnetic field makes it easier to work with bigger air gaps. For ironless motors, there is no iron inside the coils. You only have all the coils embedded in resin. And this means there is no unbalanced force, only pure thrust force, what is really good. And because of the magnetic field and the magnetic resistance, there is a low coil inductance. This means a good thing and not such a good thing. The first one is you have high response. You can apply high peak loads and you can get high acceleration. You can react very fast to disturbing force, changing loads, accelerations, and so on. But as a result, you need a good control system, not to have the moving part not under control. And also because the construction system is with a coil inside and two magnets, one on each side, to have this balanced force, there are more parts. So it's a little bit more expensive. There is also the possibility of doing iron core symmetric construction to have no unbalanced force, but then you add a lot of more components. So the result of this analysis was that ironless solution is the most adequate for variable speed drives. So okay, we now have the technology, we have selected the motor construction, then how we apply this to the architecture of a moving walk. First of all, in high-speed trains, you have the coil in the train, and then you have the magnets all around the rail. That's the logical approach for rails. But here we have hundreds, thousands of moving parts, and if we place the coils there, we have to apply wiring to there and apply current. So it's better to think the opposite way. We put the motor in the pallet guides, which are stationary, and then we place the magnets on the moving part, because you don't need any wiring. Also, there are other issues to take into account. For example, the control, you control every motor and you tell the motor what to do, what force to apply. So you cannot have two magnets. The magnets are on the pallet, so you cannot have two magnets on the same motor, because every pallet may have a different load need because of the load on top, or maybe because they are in different positions and they need different speed profiles. So also you need to close the coils, the motors, put them as close together as possible, because the efficiency and the force you get increases when you cover the magnets and the coils a lot. Magnets are going through, they are inside one coil, they are inside another coil, and the biggest the coverage you have, the better the system works. Of course, you cannot place them touching because there will be thermal effects and so on, but you have to leave the smallest possible gap. Okay, now we have no technology, the motor, we know where to place all the things, but there are more issues to understand. And first of all is, how can we control the system? We want to give the pallets a speed profile, we want to accelerate them, so we can, because we know where the motors are, where the magnets should be, we know the theoretical position of every pallet. But now we have to compare that with real position to feedback all the system. The best way should be, if we start from scratch, would be to have an absolute encoder all around the moving wall, and then have sensors in the pallets, so they are reading the position. But again, this will lead to having to wire all the pallets, and it's impossible. So we thought in a different way. We have a double sensor, we thought about a double sensor solution, in which you have a signal that tells the coil when the magnet is entering in that motor. And then you have an incremental encoder telling which distance has the magnet gone into the motor. So with this, we know the positioning of all the elements. But this is good for every coil, but how to make the full synchronization of the system? And that's another challenge. One idea could be to have a master system that is sending information to all the inverters that control all the coils. This could work, but this would mean a lot of information being transported from from the central system to the coils. And this would mean a delay, and you cannot afford that. So our approach was to make a decentralized system. So we get the kinematics of the system, the speed that the pallet should have in all the positions, and you enter that information into the inverters of every coil, because they have to do exactly the same. Every time a pallet arrives, you have to accelerate or you have to keep the speed at this rate. So the only thing the master system has to do is to synchronize the clocks of all the controller of every coil, so that all the kinematic bits, they match together and they form the overall speed profile. And this is it mainly. I will go quickly through the conclusions of the study. We have identified a gap and a need for public transportation systems, for continuous systems with high capacity for distance from 200 to 1,500 meters. We have gone through different approaches in the past from different manufacturers, some more successful than others, and also the one that is currently open to public. We have identified a technology that can simplify existing constructive systems. This is a linear motor technology. We have gone through the different type of motors. We have gone through the architecture of the system. We have also gone through the control systems and also through the synchronization of the drives. And that's all from our side. Thank you very much for your attention, and we will be glad to answer your questions if you have any.